Hello students, welcome to Sri Jayendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 9 of a unit moving charges and magnetism. So let's begin with today's class. In today's class we are going to discuss about the magnetic force on current carrying conductor. So let's begin. It's a magnetic force on a current carrying conductor. So through experiment Ampere has derived one of the relation that when current element ideal is placed in a magnetic field B, it is experience a certain force, and that force could be represented by I into dl cross B. I repeat, that force is I into dl cross B. So let's understood that this is the external magnetic field. This would be the ideal segment. Then df would be within the plane of the paper, because these two have been vector multiplication. These two are having a vector multiplication, and when these are having a vector multiplication, the resulting vector would be perpendicular to the each vector. So what I understand from this, that current in a element in a magnetic field does not experience any force if the current is in it parallel or anti-parallel with the field, because this is something like this is df equals to I dl into b into sine theta. So if we integrate this something like this, yes, it would be a b, sorry, it would be an f equals to b I l sine theta. I hope this is clear. So if current element and magnetic field both are parallel or anti-parallel, that means either theta would be equals to 0 or theta would be equals to 180 degree. This force would be a 0. One thing, when when current element in a magnetic field experiences maximum force if the current in it is perpendicular with the field. So if theta is equals to 90 degree, the force acting would be the maximum one. Now let's have a look what force and which kind of force it is. So we understood from the previous discussion that magnetic force on current element is always perpendicular to the current element vector and magnetic field, because it is because it is the cross multiplication. So we can have this dfm, it's an perpendicular to ideal, as well as this force would be perpendicular to b. This is the case, this would be always true. Now total magnetic force on straight current carrying conductor in uniform magnetic field can be calculated as, we have the relation of dfm. If I integrate this, then I will have an fm, and I am going to integrate this from initial length to final length. If I understand carefully that initial length to final length, that would be given as the length of the conductor only, and that is fm is equals to I into L cross B. Is it clear? This is fm is equals to I into L cross B. I hope this is clear. Yes, where L this is very important, where L is the initial to final vector addition of dl. This is vector sum, of all length elements from initial to final point, which is in accordance with the law of vector addition. So this L is the length of the conductor. I hope this is clear. Is it clear? Is it? Great. Now it was the case when we were discussing about the length when it was a straight wire, but let's assume that total magnetic force on arbitrary shaped current carrying conductor when it has been placed in uniform magnetic field B. Now what I need to do is I need to do the same thing, that integration of dm, that would be equals to I into integration of dl from initial to final. This is B. So this magnetic force that would be equals to I into bracket L cross B. Now, let's suppose this is having an arbitrary shape, as you can see it from here. This is having an arbitrary shape. So when it is having an arbitrary shape, what you need to do is you need to make a straight wire from initial position to final position, something like this. Take that length as the length element. I hope this is clear. So you are going to have a straight wire. You are going to have a straight wire when wire is of certain arbitrary shape, and if it is of certain arbitrary shape wire, you are going to take as initial position to final position as its effective length. So when I used to have this L, I must understand this is the L effective. That means it is the line joining initial and final. It's a line joining initial and final point of the wire. So always remember this. This is the concept of L effective. It is the L effective, that means it is the line joining. It is the line joining initial position to the final position of the wire. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now this is just the magnitude of the magnetic field. Now let's discuss the direction of the magnetic force. You can have its direction with left hand rule, that stretch your thumb, first finger and second finger, and arrange them perpendicularly. Arrange them mutually perpendicular to each other. If this is the case, then thumb will represent the direction of force. The first finger will represent the direction of magnetic field, and a second finger will represent the direction of length element. It's a length element. From initial to final, that we have already discussed about the L effective. I hope this is clear. Is it clear? Is it? So what we need to do is we have two things, that is Fm, that we call as a magnetic force, could be written as I into bracket L cross B. This L is the L effective. It is the joining line joining initial and final point of the conductor. B is the magnetic field. And one more thing, this Fm would be always perpendicular to length element, as well as this Fm would be always perpendicular to magnetic field, and direction by left hand rule. I hope this is clear. So is it clear completely? Can we go for the numerical practice? Can we? Let's begin then. Let's suppose magnetic field is there over here, and a current element is there. Direction of current is in this direction, and the length of this conductor is L. This is the initial position, let's say A, this is the final position, and this length is L. So what I understood is this is the magnetic field B. Let's first find out the magnitude of magnetic force. It would be B I L. Yes, sine theta, where theta is equals to 90 degree, and that's why I can write this as a PIL. Now let's show the direction of magnetic field. Then use your left hand such that your first finger, second finger, and thumb are perpendicular to each other, while first finger should represent the direction of magnetic field, which is inside the plane of your paper. So what you need to do is have your pen and paper, draw this diagram on your book. Make sure that your first finger is going within the book. That means it should be perpendicular and inside to the plane of the paper. Your second finger is representing the direction of current. In actual sense, it is the direction of length element vector, but for understanding purpose, you can assume that it is the direction of current. But do not write this in theory examinations, because in actual it is the direction of length element. Please do remember this. So it is in the positive x direction. Then your thumb should represent the magnetic force in the upward direction. I could say it is in the plus j cap. I hope this is clear. Is it clear? Is it? Great. So do it quickly, do not waste time, do it fast. Let's have a look. This is the magnetic field, and this magnetic field is of B. We have a current element something like this. It's a semicircular arc. This radius is R. And from this current is going, that is of I magnitude. So let's first find it out, the magnitude. It is equals to B into I into, this is L effective. I understand that theta is 90, and that would be 1. So that we understand. Now L effective. So what you can do is, this is initial position, this is final position. From initial to final you can have one line. It is like this, and if it is this line, then this is R, that should be the 2R. So this is 2BIR. This is the magnetic force. Now again turn for the direction, do the same thing, have your first finger inside the plane of the paper. Direction of I is in positive x direction, and you will find that your FM would be in the upward direction. I hope this is clear. Is it clear? Is it? So are you ready for the next questions? Do it quickly, do it fast. Have your pen and paper with you, guys. Do not waste time. Please be in hurry. Let's have a look. Here here the magnetic field is outside the plane of the paper, and the it is outside the plane of the paper, and loop is something like this. That current is moving something like this, and this is the center, and this is the radius. Yes, at this point this is E, this point this is F. The magnetic field is B, the current is I. So the magnetic force that could be calculated is B into I multiplied by L effective, and this L effective, from this is R, this could be written as B into I into 2r. So that should be equals to 2 into b into I into r. This is the magnetic force. Now direction of it. Please be carry, please be very careful that at this point of time magnetic field is outside and perpendicular to the plane of the paper, and current is moving in the, you can say it's a negative j direction. If your first finger represents the magnetic field, second finger is correctly representing the direction of current, then your force will be in this direction. I hope you got this. It's an FM. Is it? Is it? Did you receive it? Are you sure? Are you sure? Do you have the same direction of current? Do you? Great. So let's work for the next question. Do it quickly. You are doing good thing. Very good. Keep it fast. So now the situation is the current is something like this. Yes. From here, current I. Yes. This is of length L. This is of length L. And even this is of length L. So this is the situation. This is the situation. What should I do? How could I do this? So what I understand is that let's just find it out first. The magnitude, it would be equals to B into I into L effective. L effective could be from, this is initial point, this is final point, so this is represented as 3L. So that should be is equals to B multiplied by I multiplied by 3L. Now let's time for the direction. It's a time for the direction. So how could I get this? How could I get the direction of the magnetic force? It would be in the upward direction. Is it? Yes, it is in the upward direction. So this is direction of the magnetic force, Fm. I hope this is clear. Is it clear? Is it? Got it? Great. Now let's understand the next situations. Let's suppose a complete circle is there, and this is the radius r. Current flowing is the clockwise. You want a magnetic force. What it would be? First find it out the magnitude, and then we will look for the direction. So how could I do this? How could I do this? So it's an Fm is equals to B into I into L effective. Yes, this magnetic force is equals to B into I into L effective. Let's suppose understood that you have begin your motion from here. That means you have started your point from here. Then you are going to rotate it and you are landing on the same point. So in this case, the Fm equals to 0, because you can say so that L effective would be 0. You can say so to understand purpose. But what is the correct reason behind it? What is the correct reason behind it? Let's check it out. That let's assume this coil. Let's assume this coil in two segments. That I'm going to divide this into this two segments. That's is something like this. A magnetic field is inside the plane, and if I understood this, this is the direction of I, and this is the 2r. This is the 2r. So if I understood this is the first segment, this is the, let's say this is the second segment, and if I have done this Fm, this F1 I said it's a Bi into 2r. What would be the direction of this Bi into 2r? Yes, it is in the upward direction. You are correct. So this force, it's a Bi into 2r force is acting in the upward direction. Now let's just choose the second wire. Let's just choose the second segment, or the, that is the lower half of the wire. It is something like this, and the current is moving in this direction. So if current is moving in this direction and this is the radius r, current is I, so the magnetic force on this, It is again the bi into 2r. Now what would be the direction? Please check it out the direction carefully. Yes, what was it? Yes, it is in the negative x direction. This is F2. So if you observe this carefully, a certain force is acting, on the upward direction, which we call as an F1. Certain other force is acting on it, it's an F2. And this F1 and F2, these two are the equal. Now you can do one more thing, that you can even divide this. You can even divide this into this segments. Let's try to understand that this is the magnetic field and this is the segment. This is the segment through which current is passing. This is radius r. So now as this is radius r and that current is passing, what amount of forces is acting? So this is magnetic field, this is force. So this, if I write this as an F3, that would be equals to B into I into 2R. This is equals to B into I into 2R. And direction of that force, what would be the direction of that force? What it would be? Yes, it is on the right hand side, positive x direction, I can say. So it's an F3. Now find out the direction. Find out the direction of the second quarter. It is something like this. Current is moving like this. This is radius r, this is magnetic field B. So when current is moving like this, use your left hand such that magnetic field will be inside the plane of the paper. Magnetic field will be inside the plane of the paper, and 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 current is moving in the upward direction. So if you hold this situation correctly, your force should be in this direction. Again the magnitude would be the same, it's a bi into 2r. So you can have this, that F1 F2 is there, and so the F3 is acting on this direction, F4 is acting on this direction, and everyone and each one is of same magnitude. So you can say that this F1 nullifies this F2 and this F3 nullifies this F4, so that net force on this ring is 0. So that net force on this ring is 0. So we can have one note over it. Please understood it very carefully. When current is flowing through any closed loop in one direction only, when I say one direction, I mean either clockwise or anti-clockwise, then net magnetic force on the wire is always a 0. Yes, go through it very carefully. Do not ever understood that sir has said so that if current is flowing in closed loop then the magnetic force is 0. No, I have not mentioned it. I have mentioned it that when current is flowing through any closed loop in one direction only, that means it should either flow in clockwise direction or it should flow in anti-clockwise direction. If it is not the case, this statement is not correct. So if it is the case, let's suppose if it is the case, then the net magnetic force on the wire is always 0. This is the case. I hope this is clear. Is it clear? Is it? Do you understand this fully? Now let's have one very logical question of the ring, and this is one of the favorite questions of the examiners. They said that this is the magnetic field, and let's suppose you have made a ring. You have made this ring, and let me redraw it. Yes, this is made up from certain. This ring is made up from stretchable material. If current starts flowing through this ring, if current starts flowing through this ring, what happens? What happens to the ring due to magnetic force? While I say what happens, I mean it should, when I say what happens to the ring, it means it will compress or it will expand or no change at all. So now understood fully that this is the magnetic field B and current starts flowing through it. If current starts flowing through it, I understood completely that net magnetic force is zero. But if you understand it, concept behind it that we have derived over here, that if you observe this very carefully, this part is being stretched over here. This part is going to be stretched over here. This part is going to be stretched from here, and this part is going to be stretched from here. So if you understand this, someone is there who is going to try to expand it. So this is the correct answer. This is the logical question. Very beautiful question. I hope this is clear and you understand it too. Is it? Is it? Do you understand this? Are you sure? Are you sure? Great. Now let's work for the next question. This is the magnetic field. Magnetic field is given, and it is somehow given like this, that this is the center, this is the radius r, current is flowing in this direction and current is flowing in this direction. What do you need to do? You need to find out net magnetic force. Find out net magnetic force on the loop shown in figure. So how will you do this? How will you do this? Because look at this. If you understand that yes, this is closed loop and answer would be 0, you are making a mistake over here. So does current is flowing in the same direction? Yes, if I observe this situation in two different segments, then my first segment should look alike something like this. It's a semicircular wire having radius r, and my second segment would be look like this, that it is the it is the wire having length of 2r. Yes, so if I apply a force on this semicircular loop, it's a b into I multiplied by 2r. This is Fm, it's a bi into 2r, and that force is acting on the which direction? Use your left hand and let me know. In which direction does it acting? Sorry, in which? Yes, positive x. So this is Fm. Now let's find out the direction on this wire. Let's find out the direction on this wire. That magnetic field is inside, current is moving in positive x direction, and the magnetic force should be in the upward direction. So even here, magnetic force is acting in the upward direction. It's Fm is equals to Bi into 2r. So if both are having a vector in the same direction, I must consider F net as the Fm of 1 plus Fm of 2. Does it clear? So in totality, that should be, it should be 4 BIR. This is net magnetic force. This is net magnetic force acting in the upward direction. Let's assume it as a J cap. So look at this. Why I have taken this example? Because this is even the closed loop. But here the net magnetic force is not zero. I hope you understand this. So it is not the case that if closed loop is there, answer would be zero. No, it is not the case. Yes. So please do not misunderstood this, that if it is a closed loop, then the force would be zero. No. If it is a closed loop plus current is flowing in any one fashion, that means either clockwise or anti-clockwise, then the answer would be zero. Is it clear? Is it clear? Is it any doubts in this? Anything? Are you sure? Great. Let's work for the next question. Do it quickly. You are doing good thing. Let's suppose a magnetic field has been set up and current carrying conductor, it is something like this. This is of 3 meter. This is of 4 meter. Current is flowing. Current is flowing, such as from here to here. This is magnetic field P. What I want find out magnitude and direction of magnetic field. So how will you do this? How will you do this? Take your time and think before you act. So what you need to do is you need to connect your initial point and final point. This is initial, this is final. If I connect this, this would be the phi according to the Pythagoras. Yes, it's a right angle triangle. So this should be the length vector. I hope you understand this. And if this is length vector, magnetic field is inside the plane. Arrange your left hand such that first finger represents the direction of the magnetic field, and the second finger will represents the direction of length element. Then your thumb, which is indicating in this direction, mine is indicating on this direction. Which one is yours? In which directions your thumb is representing? Yes, is it the same? Great, you are doing good thing. Next, it's an Fm is equals to B into I multiplied by L effective, which is phi. So this is equals to phi into B into I, Newton. I hope this is clear. So it is not the case that every time it would be only in I direction, or it would be in J direction, and it would be in plus k cap or minus k cap. No, it could be in the plane as well, that covers a certain angle of x as well as certain angle of y, when this is true for x, y, z, any plane. Is it clear? Is it clear? Is it clear up till now? Great. Now let's focus on this question. Let's suppose they will ask that this is a circular loop. This is a circular loop, and radius of this circular loop is r. So what they ask is that find out net magnetic force as well as tension in the ring or tension in the wire. Suppose current is flowing in this direction. So if current is flowing in one fashion only, you can observe this very carefully, that current has started from here, it would be here, it would be here, it would be here, and so on. So here the current is moving in the clockwise direction. That means it is traveling, it is moving in only one direction. And when it is moving in only one direction, your Fm, that is the net magnetic force, will be equals to 0. So my first task is over, and that I know that can be done very easily. Now only the thing I have been stuck is how to calculate the tension in this ring. How to calculate a tension in this ring. So to get the tension, we can have this kind of situation, that you can cut this ring, and you can assume that this is the rigid support. And with this rigid support you have a semicircular segment, something like this. And in this current I is flowing. This is the center, this is R, and this ring has been attached by two strings over here, you can see. So yes, and magnetic field has been arranged in this region. So what you understood is that magnetic field has been arranged in this region, and this ring has been cut it in two segments, and one of the segment has been attached with the string so that I can have a value of intention. So if you calculate the magnetic force, that would be is equals to Fm, and this Fm could be written as B into I into 2R. I hope this is clear. Is it clear? Is it? Great. Now as this force is acting in the upward direction, this magnetic force is going to stretch this, and due to this there is a tension developed in this two strings. So T net, or the T total, would be equals to 2T. So this 2T would balance this if this ring is not going in the upward direction. So I can write like this, it's a 2T, that should be is equals to Bi2R, and this 2 can go on, and this T is equals to B into I into R. This is the tension force. This is the tension force that is acting on the ring. Is it clear? Is it? So do you understand this fully? Do you understand this fully? Any doubts in this? Any doubts in this? Is there anything? Is there anything? Are you sure? Are you? Are you sure? Great. Let's have one more question. Yes. A square loop is there. Square is having a side of L by L. Magnetic field is of B. Current is flowing in this. It's something like this. I need to find out Fm, what it would be. Tell me. Yes, it would be a 0. This Fm would be a 0, that we know. Why? Because first thing, it is a closed loop. Second thing, it the current is flowing in same fashion throughout the loop. And if current is flowing in same fashion throughout the loop, if current is flowing in same fashion throughout the loop, that means net magnetic force will be 0. But let's suppose if someone asks me that, let's say this is C, this is D, this is E, and this is F. If C, D, E, F, these are the different segments, and someone asks me that find out the force acting on the CD segment, what should be my answer? So I understood that FCD would be equals to B into I into L. What would be the direction? So keep your right hand, keep your left hand such that first finger will represents the direction of magnetic field, second finger will represents the direction of current, and the force will represents the direction of force. So thumb will represents the direction of force. This is F. If you find it out this, if you find it out magnitude, then FCD, FDE, FEF, or FCF, this all are same in magnitude, that is equals to B into I into L. Direction wise, on this force is acting on this, on this force is acting on this, on this force is acting on this. That's why net force is going to be 0 all over. I hope this is clear. Is it clear? Is it? Great. Let's work for the next question. It says that a wire is bent as shown in the figure, carries a current I, and it has been placed in a uniform magnetic field of magnetic induction B that emerges from the plane of the figure. It is moving outside. Yes, perpendicular and outside the plane. Calculate the force acting on the wire. Great. How should I do this? How should I do this? So let's suppose this is initial point, this is final point. I need to make a wire from here to here. This is R, and even this would be the R, so this would be the R. So this is R. This is 4R. So the magnetic force could be written as B into I into 4R. This is the magnetic force. Now direction. Direction of magnetic field could be given as that this is the direction of length element, but magnetic field is outside the plane of the paper. Magnetic field is outside the plane of the paper, and current is length element is in this direction. So magnetic force could be in that. Look at this, that we have Fm, that is equals to I into bracket L cross B. This L is in I cap, this B is in the K cap. Yes, if we assume that this is I, this is J, and this cross or dot could be the K cap. Yes, plus K or minus K. Yes, so dot could be considered as a plus K cap. So now the situation is, this is I cross K, and when it is I cross K, something like this, it's an I cross K would be equals to minus of J. So this Fm should be equals to minus of 4 IBR J cap. That's it. Is it clear? Is it? Are you sure? Are you sure? Is it clear? Is it? Great. Ready for the next question? Are you ready? Ready? Great. Let's have a look. It says that a square of side 2 meter is placed in a uniform magnetic field B of 2 Tesla in a direction which is perpendicular to the plane of the square and which is inwards. Equal current I is equals to 3 ampere is flowing in the direction as shown in the figure. Find the magnitude of the magnetic force on the loop. So this is a 2 by 2 square. Its length is 2 meter, and as it is a square, it would be having the same length and same width. current that is of I should be equals to 3 ampere. So 3 ampere current is flowing through this loop. What you need to do, you need to find out the magnitude of the magnetic force on the loop. How will you do it? So let's understood that this is the initial point, this is the final point. So this should be the initial to the final. This is the initial point, this is the final point. So again this should be the initial to final point. I hope this is clear. Is it clear? So the situation is something like this, that if this is the situation, this is 2, this is 2, this length should be 2 root 2. Yes, this length should be 2 root 2, and this is the initial point, this is the final point. So this is Fm should be is equals to B into I into 2 root 2. Currently I am working for the magnitude only. So this is equals to 2 Tesla. Current is of 3 ampere multiplied by 2 root 2. This is 2 3s are 6 6. This is 2 3s are 6 6 2s are 12. This is equals to 12 root 2. But this is due to a single wire only. We have 3 such wires. So F net would be equals to 3 into Fm, because for everything current is same, magnetic field is same, so the force acting would be the same. So this is 36 into root of 2 Newton. I hope this is clear. This is clear. Is it? Is it? So can you do this? Can you? Are you sure? Can it be done? Great. Let's work for the next question. It says that a metal rod of mass 10 gram, yes, and length 25 centimeter. So this is a metal rod having a mass of 10 gram and length is 25 centimeter, is suspended on 2 springs as shown in the figure. Okay, the springs are extended by 4 centimeter when a 20 ampere current passes through the rod. When 20 ampere current passes through the rod, it rises by 1 centimeter. Determine the magnetic field assuming acceleration due to gravity to be 10 meter per second square. So what does it says? What does it mention over here? It says that the springs are extended by 4 centimeter and it was the initial equilibrium, but no magnetic force were there. But let's just calculate that what amount of forces are acting on the system, and then we will go for the numericals. That this is the rod, and when magnetic field has been set up, it is something like this, that what would be the direction of magnetic field, because current is moving in this direction. This is the battery, so this is the positive to negative current is flowing. So this Fm is going to act on this direction, Fm. Yes, it passes through the rod, it rises by 1 centimeter. It has been rises by 1 centimeter. So if if it has been compressed due to this Fm, then I must apply Kx. It's a spring force in this direction. This is Kx, this is Kx. One more thing, this would be the mg. Yes. So for the equilibrium, I should understand that this Fm should be equals to 2kx plus mg. Now I am having an every value, it's a bil, that should be is equals to 2kx plus mg. So x should be, sorry, I need to find out the b. So b should be 2kx plus mg divided by I into L. Do not forget to convert this and mass, because they are in the CGS systems. But is it clear logically? Does it clear? Are you sure? Great. So get it done by putting a value. Now look at this, go through the data. What does it say? Is it says a wire A B C D E F. Okay, so begin from A to B, B to C, C to D, D to E, E to F. Okay, with each side of length L is bent as shown in the figure, and carrying a current I is placed in a uniform magnetic field B, which is parallel to plus y direction. Okay, so what I need to do is, what is the force experienced by the wire? Okay, go through the figure carefully, that this is the y-axis, this is the z-axis, and this is the x-axis. Your wire is beginning from here and it is ending over here. So from beginning to ending, it should look like this, that this is the length segment of the wire, and it is moving in x direction. You can see this, it is moving in the x direction, and magnetic field B is parallel to y direction. So first let's just calculate the magnetic force magnitude, which could be given as B into I into L effective. If I connect this point to this point, because it is the initial point to the final point, I would have a value of L. So this would be B into I into L as per the value. And what would be the direction? So my I vector, my length vector, my length element is in I cap, and my magnetic field is in plus y, that means it is in j cap. So when I perform Fm, which could be I into bracket L cross B, so it is the case of I cross j. This is I, this is j, this is k. If I perform I cross j, I will have a k. So this magnetic force should be is equals to B I L k cap. I hope you got the same answer. Did you? Did you get the same answer? If no, then do you understand it completely? Do you? Do you understand it? Great. Let's look at this question. This is a very good question. Suppose they have given that this is infinite current carrying conductor, and the current they have given, it's the I1, and one more conductor is given over here. This is, let's suppose, current flowing through it. This is I2, and this is, we can say, this is the finite wire. So what they are supposed to ask, let's have a sec. It says that, what, find out magnetic force acting on the finite wire due to fixed infinite wire shown in the figure. So this is the question. Now you tell me how to deal with this. How could I do this? It says that one of the infinite wire is given. And what I need to find out, what I required is, I need to find it out the magnetic force acting on this finite wire due to this infinite wire. How could I do this? How should I? The problem is that let's suppose, understand that, let's suppose if I take this wire, if I take, let's suppose this is distance r, and a length of a finite wire, it's an a. So if I take this as a distance, my magnetic field or force is, it's a BIL. F is equals to BIL sine theta. The magnetic field, let's suppose mark this as a point 1. magnetic field on first reason is mu naught I divided by 2 pi r, and if I mark this as a second reason, the magnetic field over here, it's a mu naught I divided by 2 pi r plus a. So if you observe this carefully, you might got that at every segment magnetic field is keep changing, and if magnetic field is keep changing, what I need to do is I need to take a help from the integration. I hope you understand the scenario. Is it is it do you understand this? So what I need to do is I cannot apply directly f is equals to bl sine theta and let it done. What I need to do is that let's understood that this is the case of of variable magnetic field at every instant. Yes. So what I need to do is, let's have a look. Let's assume that this is the infinite wire, current is I1, and this is a finite wire. This is a finite wire through which current is flowing, and that current is I2. So what I need to do is, let's suppose if I choose a certain segment, width of that segment is dx from this, and this is kept at the x distance x. So if I write down the magnetic field over here, what I can write is it's a df that should be is equals to mu naught into I1 into I2 divide by 2 pi x dx. I hope this is clear. Is it? Yes, we have written only this thing, that f is equals to b into I into L. This b for the infinite wire is the mu naught into I divided by 2 pi r multiplied by this b is given by I1. This is the second wire, it's an I2 multiplied by L. Yes, this is the standard formula on which we are relying. So this is df is equals to mu naught I1 I2 divided by 2 pi x into dx, and now I need to integrate this. As I understood that this is r, and this is the length of this finite length conductor, it's an a. So if I integrate this on both the sides, on here I would get an f, but on here I will be having, let's have mu naught I1 I2 divided by 2 pi on the aside, and I need to do integration of dx by x. From where to start integration? I need to integrate it from r, from this distance to r plus a. I hope this is clear. So let's do it. It's a mu naught I1 I2 divided by 2 pi integration of dx by x, which is an ln x, starting from r ending at r plus a. So that should be is equals to mu naught I1 I2 divided by 2 pi into bracket ln r plus a minus ln of r. I hope this is clear. So when I have written this, I understand that ln it's a lateral log, a subtraction of log is the differentiation. So this f could be written as mu naught I1 I2 divided by 2 pi multiplied by ln r plus a divided by r. This is the final answer. This is mu naught I1 I2 divided by 2 pi r. I have missed out it. Yes, it's a mu naught I1 I2 divided by 2 pi r. Mu naught I1 I2 divided by, it's mu naught I1 I2 divided by 2 pi x into bracket ln r plus a divided by r. I hope this is clear. Is it clear? Is it? No, I made a mistake. Yes, it's a mu naught I1 I2 divide by 2 pi into bracket ln r plus a by r. Is it clear? I hope this is clear. Is it? Great. So now shall we move to the next topic? Shall we? Will you be able to solve this kind of questions? Will you be? Great. Now let's move. look at the next topic. It says that find out force force between two parallel current carrying conductors. So if I have kept two wires which are parallel to each other, I need to find out the force between these two wires. So according to the Savart's law, there exists a magnetic field due to a current which carries a current, and further an external magnetic field will exert a force on the current carrying conductor. Thus, if two current carrying conductors placed near each other will exert magnetic force on each other. Yes, so this is my first conductor, this is my second conductor, both is carrying certain current. Let's suppose this is carrying current I1 and this is carrying current I2. Let's suppose this is I1, this is I2, and they have been separated by a distance d. So now if each one of them is carrying a current, that means each one will be having magnetic field around them. I hope this is clear. So let's understood that A and B are two long parallel conductors, and they carry parallel currents termed as the IA and IB respectively. Now conductor A produces the same magnetic field BA at all points along B. So from the Ampere circuital law, magnetic field at A would be given as mu naught into IA divided by 2 pi B, 2 pi D, I mean. Yes. Now same way conductor B carrying a current IB, and it will experience a force due to BA. So then the force on A due to B could be written as it's a mu naught into IA into IB into L divided by 2 pi D. Similarly on a same manner, F on BA, that would be equals to minus of mu naught IA into IB into L divided by 2 pi D. Is it clear? So they are having a force due to magnetic field of each other. Look at this. This is, let's suppose, have a generalized term of it. It's a I1, it's an I2. If these two are there and they are having a flowing a current through them, I1 and I2, then force per unit length could be written as mu naught into I1 into I2. Let's assume this, they are separated by distance d, divide by 2 pi d. This is the generalized formula that you need to remember. This is force per unit length when two conductors are placed parallel to each other and they are having certain current through them. So we understood that both the currents are opposite to each other, and that's why parallel current attract and anti-parallel currents repel. That means if two currents are something like this, it's a I1, it's an I2, then these two are going to attract each other, while if anti-parallel currents are there, this is I1, this is I2, they are going to repel each other. Let's suppose this is distance d. I hope this is clear. Is it clear? So what you need to remember is if two current carrying conductors are there and they are having a current and the direction of flow of current are same, that means they can be considered as a two parallel current carrying conductors, then they will attract each other. And if two conductors are there, they are having a current but direction of the current flowing in each of them is opposite to the second one, then they will repel each other. I hope this is clear. Is it? So are you ready for the questions? Are you? Let's have a look. It says that, let's suppose this is I1, this is I2, this I1 is of 3 ampere, this I2 is of 4 ampere, and the distance between them is the 5 meter. So let's suppose this is conductor 1, this is conductor 2. So the question says that find out magnetic force on second conductor due to first conductor. So let's do it. So what I can do, if I have been find out the force, so I can write like this. It's an F by L, that could be written as mu naught into I1 into I2 divided by 2 pi t. So this is F has been asked. So this is equals to mu naught multiplied by I1. It's a 3 multiplied by 4 divided by 2 pi multiplied by 5 multiplied by length L. So this is this mu naught. It's a 4 pi into 10 to the power minus of 7 multiplied by 3 4s are 12 divided by 2 pi into 5. Yes, this is 2 pi, 2s are 5. This is 12 2s are 24. 24 by 5. It's a 24 by 5 into 10 to the power minus of 7 into L Newton. This is the force they are acting. Now as you can see that both are having a current in the opposite directions. So they are going to repel each other. This is force due to first on the second wire, and this is force due to second on the first wire. Yes, they form an action reaction pair that is to be remembered by you guys. I hope this is clear. Is it clear? Is it any doubts? No? Great. Let's work for one more question. It is something like this. Let's suppose this is I1, this is I2, this is I3, this is 2 meter, even this is 2 meter. Yes, these two are the 2 meters. So this says find out force acting on second wire. This is requirement. This is the first wire, this is the second, this is the third. So what do you need to do? You need to find out a force acting on the second wire. This is 2 ampere, this is 4 ampere, and this is 3 ampere. This is given. So what I need to do is, first I need to consider that force on 2 is acting by force wire 1. So it's a force on 2 due to wire 1. It's a mu naught multiplied by I1 multiplied by I2 divided by 2 pi d into L, because it's a force per unit length. So this is equals to 2 pi. This is mu naught multiplied by 2 multiplied by 4 divided by 2 into pi into 2 multiplied by L. This is F21. Now I need to find out the force on the second wire due to the third wire. That could be given as mu naught multiplied by I1 multiplied by I2 divided by 2 pi d. This could be written as 4 pi multiplied by, this is 4 ampere. Sorry, it's a 4 pi into 10 to the power minus of 7 multiplied by this is 4 ampere, this is 3 ampere, divided by 2 pi into d. It's a 2. I hope this is clear. Is it clear? Multiplied by length. Yes. So this is equals to 4 3s are 12 into 10 to the power minus of 7, because this 4 pi has gone, and this is 2 pi 2s are 4 pi multiplied by 10 to the power minus of 7. So this is 8 into 10 to the power minus 7, and this is 12 into 10 to the power minus 7. Now the question is that current in this and current in this are in opposite direction, so it is each other, so they are going to repel each other. And when they are going to repel each other, then I should focus on the direction that this is the force on the second due to first, and this is the force on the second due to third, as the direction of both the forces are opposite to each other. So F net could be written as F23 minus of F21. This is 12, this is 2 4s are 8, so this is 12 minus 8 into 10 to the power minus of 7 into length L. Yes, this was length L. And while I write this, it's a 12 minus 8, it's a 4 into 10 to the power minus of 7 into L. Is it clear? Is it any doubts, any confusion over this? Anything Any doubts, any confusion over this? Anything? Are you sure? Pretty sure? Great. Now, one more logical question to this is that let's suppose what they are supposed to give you is that this is the current carrying conductor. Let's suppose this is I, and one of the loop is there, something like this, and through this loop one current is flowing, that let's suppose this is I1, this is I2. Yes. So this, so the question they ask is let's suppose even distance is given, this is A and this is the square of length. Question is that will this coil is being attracted or repel by this infinite length wire. So they ask what would be happen to this conductor, that will it attract or will it repel. So what I understood is that force would be acting on this wire and this and this and this. So let's name them. It's a first, it's a second, and this is the third. So force between 1 and 2, that could be written as mu naught I1 I2 divide by their separation, it's a 2 pi a. And the force between 1 and 3, would be mu naught I1 I2 divide by 2 pi, and separation between them it's the L plus A. I hope this is clear. Now what I need to understood is that this and this, the current in I1 and I2 in this second wire, first wire and second wire, are in the same direction. So if they are in the same direction, so they are going to attract each other. This is something like this. But force between first and the third is such as they are going to repel each other. So first wire and second wire are going to attract each other, first wire and third wire are going to repel each other, something like this. This is first and this is third. So will effectively it will attract or will effectively it will repel. If I understood that these two forces are there, now which one is dominating? Because this is the distance which is 2 pi a, this is a distance which is 2 pi L plus a. So I am sure that as distance is higher in this, the force will be lower in this. So F net will be equals to F12 minus of F13. So 12 wants that that loop is going to attract. So that's why loop is going to attract towards infinite length wire. I hope this is clear. Is it clear? Is it? So please do remember this. This is the one of the question that examiner wants to ask. Yes? Great. Now let's define one thing. It's an ampere. Let's define the ampere. When we say SI units of current, yes, we include this in the 7 fundamental quantities. So we understood that FBA should be equals to FBA by L, and that should be equals to mu naught into I1 into I2 divided by 2 pi d. Here we have taken I1 and IB as an I2 as a IA and IB, and let's suppose that IA and IB is the 1 ampere. So we can say that the ampere is the value of that steady current which, when maintained in each of the two very long and straight and parallel conductor of negligible cross section and placed 1 meter apart in vacuum, would produce and each of this conductor a force of FBA, and FBA would be the it would be having a value of 2 into 10 to the power minus of 7 Newton per meter, because this is force per unit length. I hope this is clear. This is because this is force per unit length. So thus we can define an ampere. This could be helpful. This could be helpful in your school examinations. I hope this is clear. Is it clear? Is it any doubts? No? Great. So we have been asked that SI unit of current. Yes, it's an ampere. Second, two current carrying conductors, when they are placed near each other, will exert electric force, magnetic force, gravitational force, or electrostatic force. Yes, they are going to apply a magnetic force on each other. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's just wind it up this session over here. This is all about the force acting on the current carrying conductor. Please make practice of questions based on this topic. This will help us to solve the questions fast and accurately. Thank you. Have a good day. Take care. Bye bye.